Howdy. We're ready for our discussion on Chapter 8. So, in Chapter 8, uh, acid, bases, oxidation, and reduction. A lot of terms going on here, and one skill. So, one important skill, a lot of terms we want to be familiar with. And so, uh, we'll be learning about titration. We talked about that in the lab. This idea of acids and bases, their reactions. The only real skill we have to worry about is this pH. So let's start with these definitions. So I've got a series of definitions here for the acid and base, the Arrhenius theory, the Bronsted-Lowry theory. But let's break it down a little bit easier here. An acid, two definitions for it. I don't care if you know whose names goes with each of these. So the first definition, it produces H plus in water. Now this idea of H plus is a proton. H plus is a proton. So we're taking hydrogen 1 and we're losing an electron. So all that's left is a proton. Remember, it has no neutrons. Okay, so H plus is a proton. So we make that in water. It's an acid. Second definition then is it is a proton donor. It gives away a proton. Uh, this second definition removes the requirement of water and helps makes life a little bit easier. Then a base would have two definitions. One is it produces hydroxide, and that's one of our polyatomic ions in water. Now, the problem here is we've got this requirement of water, and we also have this producing hydroxide. Not every base actually produces hydroxide in water. So that definition we had to expand then, and it is a proton acceptor. It'll take a proton. All right, and so hydroxide is actually very good at accepting a proton. All right, so that's our definitions then. Um, and when I come back over here to my definitions, I see hydronium ion, H3O plus, is being what's made when we have H plus in water. So keep in mind, our water has two lone pairs, and this side is slightly negative, and this side is slightly positive. So if I have an H plus floating around, it is not going to stay out there very long at all. It's almost instantaneously, if my solvent is water, grabbed up by our water and turned into hydronium. All right. Now this is an acid. It will continue every time it hits something. It can give off an H plus. And so for our discussion, if we have a proton and it's in water, it's always hydronium. It'll always be hydronium. But we'll use them interchangeably. The equations are easier to memorize with H plus, but you'll occasionally see me write it out, especially on, for instance, when I go to something like our helpful equation sheet, and I look on here, I see H3O plus used instead of H plus, and that's just because it's more correct, and we use it. You'll see me having it written down in a large part in case somebody else needs to use my notes and they want to be able to quickly tell, you know, it just looks nicer, I guess. Now, water can do two things. So here's my water, and I'm going to take away H plus. I'm going to take an H plus from that. So we're going to lose H plus. And what job would something have if it lost H plus, if it gives it away, it donates it? That's an acid. And then, so if it gave it away, I'd have OH minus left. I'd have my H plus, and I'd have my hydroxide left. So my acid Water can serve as an acid and give away a proton. Now water can also accept a proton. So if I take a proton and give it to H2O, so here it's playing the role of a base. And then on this side, I would have 3 hydrogens now, and an overall positive charge. I'd have hydronium. Now, and so an acid and a base, it's amphiprotic. Protic, talking about this proton, it can gain and lose. You've seen this prefix amphi before. It may take a little while for you to realize it, but it's an amphibian. It does both water and land. So amphiprotic is both an acid and a base. Now I'm also going to use these same kind of ideas and look at this. You'll notice on this side, my OH minus, that's a base. All right. And then when water was a base, it formed this acid over here. So we'll add some fancy word for this, conjugate base and conjugate acid. So every acid has a conjugate base, and every base has a conjugate acid. And it'd be after it has done its job as either an acid or a base, what's formed. All right. So we'll use those terms a lot. This idea of conjugate acid and conjugate base. And the next thing we got to learn is this idea of acid strength. Now, acid strength is not related to its concentration. Now, how dangerous it is might also be related to the concentration. But this is really an idea of whether something dissociates or whether it forms an equilibrium with its. So here I have HCl, and it's reacting with water. Here's my H3O plus. All right, there's my hydronium being formed. All right, that's the H plus that came up from my HCl. And I have the Cl minus. This would be the conjugate base of my acid. Now the water here is playing the role of a base. And so it has a conjugate acid on this side. And so if this reaction goes to completion, in which I don't have any of these HCl left, if I don't have any of that left at all, it completely dissociated, it's called a strong acid. If instead it sets up an equilibrium, it will be called weak acid. So let's just get a list of these. So my strong acids include hydrochloric, nitric, and sulfuric acid. Now we start to see a trend on these. So you'll notice that these end, if it's an acid, it ends in ic, an acid. All right. So HBr would be hydrobromic acid. HI would be hydroiodic acid. All right. And then nitric and sulfuric sometimes gave us some trouble. But you know this one, that's nitrate. And I add enough hydrogens to neutralize it. And when I neutralize it out, then it's going to be HNO3. That'll be my nitric acid. So if I take sulfate, it's a -2 charge. It's going to take 2 hydrogens to 2 protons to neutralize that out. And so that's why we get H2SO4. All right. Now, this is a nice way of keeping up with the polyatomic ions. You just add the hydrogens until you get to your neutral charge. That's a nice way of keeping up with the names of these. When I was a student, we did a song by Tourniquet. Tourniquet, and it's called Acid Head. And there's a lot of intro to the song. It's not a great song, but yeah, I'll never forget it. It helped me through the test. The first bit of it was Johnny was a chemist's son, but Johnny is no more. What Johnny thought was H2O was H2SO4. And I could remember that was sulfuric acid from there every time after. All right. Now strong bases are going to be a metal with a hydroxide. You want to be careful. It has to be a metal. So if you see something like this is an alcohol, not a strong acid, not a strong base. All right. We'll even see stuff like acetic acid. Looks like that, and it has an OH, but it's an acid. This is acetic acid. So what are we looking for then? It has to be a metal. Lithium hydroxide, potassium hydroxide, sodium hydroxide. The last two are the only two that we usually use because they're soluble in water. All right, so it has to be a metal plus the OH. So don't just look for the OH. They can be sneaky on some of this. All right. So we've got strong acids, strong bases. So then let's look at some weak acids. The two weak acids we'll be looking at. Here's that acetic acid we just mentioned. The acetic acid we just mentioned. All right. Then carbonic acid we've discussed extensively. So the reaction of CO2 with water forms a weak acid. All right. It can actually, it's diprotic. It can lose both protons. Okay. Weak bases, all of these, notice that nitrogen. So the main weak base we want is not actually from that list. We want to know this weak base, which remember was ammonia. All right. Now, its conjugate acid then is ammonium. Remember, more stuff, bigger name. All right. And so ammonia is a weak base, and ammonium is a weak acid. I'm sorry, is a conjugate acid of that weak base. And so, um, don't want you memorizing pyridine or aniline or methylamine. I want you knowing ammonia. All right. So we talked about conjugate acids, conjugate bases. So we can skip this lab. We're ready for then pH scale, and a pH scale gives us a way of discussing water and reactions in water. And it starts with this idea that water auto-ionizes, that water reacts with itself and it sets up an equilibrium. Because remember, so here's two waters. All right, I'm going to make this one an acid and this one a base. Now, what is the job of an acid? It donates a proton. And so what will be left behind is OH minus, and what will be formed when this does its job as a base, it accepts a proton, will be H3O plus. So water reacts with itself. This was auto ionization. It reacts with itself, and it forms hydroxide and hydronium. All right. Now, if we look at the concentrations of these, the hydroxide and the hydronium concentration is actually very, very small. This H3O plus molarity times the molarity, so this is moles over liters, times the molarity of the hydroxide is always 10 to the minus 14. Right? So these molarities, when we multiply them, is always equal to 10 to the minus 14. We don't have very much of either one of them. We've got very, very small amounts. Remember, 10 to the minus 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and then 1. Whoa. My mouse out of the way so I have room to write that. All right? So, very, very small. Now, this is so small that it's hard to say, hey, if I have 10 times the amount, it's still a really small number. It is not very scary. And so what we do is we do the pH of this. And so that pH is the negative log. Anytime you see a P, it's always negative log. So this part's the P. And then of our H plus, which remember H plus is hydronium concentration. Those two are the same. All right, so all we're doing then is negative log of these really small numbers. Why would we do this? All right, so if I have some number that's like 10 to the minus 8, and I want to know whether it's a lot of acid, more acid, or if it's more base. All right. So what this does then is the negative is there, and it gets rid of that negative sign, and the log gets rid of this base 10. So instead of having to talk about something that is 10 to the minus 8, which is this number, we can talk about in terms of being 8. Now, why is this important? Keep in mind the H plus times the OH minus is 10 to the minus 14. So the place where this would be equal amounts, where I have just as much acid as I do base, we would say is neutral. And that would be 10 to the minus 7 times 10 to the minus 7. Keep in mind you add the exponents, right? So it'll be 10 to the minus 14. So if I do the pH of that, I'll have 7. Right? And that's where we're neutral. Now, dealing with this, you can use your calculator, and you're going to hit negative log of whatever the H plus is. So I reach in, pull out my calculator, and I'm looking for the buttons to push. The log button is located over here by the 7. Right? And so you can just use the negative log, and then you can use the EE button to give you your button for your molarity there. Okay? Now, when I want to do these, I do a series of practice. There's 3 skills that we'll be using on these. So the 3 skills, this is some practice. Let's get, here we go. The 3 skills then, if I have the molarity of the hydrogen and I want pH, we can just type it right into our equation. Negative log of whatever our H plus is. Alright? Now, a lot of times it'll be easy stuff. We'll see a shortcut. I'll show you that shortcut. It makes things pretty nice and easy. Alright, so let me show you that shortcut real fast. If I had H plus concentration equal to 10 to the minus 4th, then all I have to do is the log will get rid of this, the negative gets rid of that. All I care about is the pH then would be 4. Alright, so if the H plus concentration was 10 to the minus 9th, then the pH would be 9. I'm going to take what's in this box, and that's my answer. Only if it's easy, there's nothing out in front of this 10. If there's more difficult than that, then we're going to type that right into our calculator. Okay. The next thing is if I'm reversing this reaction, then I'm going to go from pH to the molarity of H plus. It says I need to take my H plus, and I'm going to do, and we can do a bunch of algebra here and show you that. Matter of fact, I have a slide here that walks through going through and doing all this. Oh man, we don't want to do any of that. We're going to use that same idea of that trick that we just used, our shortcut, and I'm going to say, here's my 10, and then here's the box, and I'm going to take the pH and I'm going to put it in there. Now when I type this in, I can't use an EE. It's not going to let me put some numbers in there. Alright, it's going to freak out. So we're going to do this by hitting second log, and that gives us this 10 to the x button. Alright, And so second log and then negative and whatever the pH is. You type it in, it'll give you an answer. On the easy ones, nice and simple. So if my pH was 8, then I can just say my H plus concentration will be 10 to the negative 8. All right. Now, where it's more complicated is if they told me the pH was 2.5. If it's got a decimal place, you can't use the EE button. And so 10 to the negative 2.5 is not a number. And your calculator will freak out on you on that. But if I come in and I type in second log and give me that 10 to the x and put it up there high for me, minus 2.5, I can hit enter and it'll translate this. And it told me that that is 3.16 times 10 to the negative 3. Or I wrote it out in the decimal form, 0.00316. Right? And so both of those work great. The units on that would be capital M molarity, moles per liter. Okay. Now the only one that's different that doesn't use that pH formula is if I have this idea of going back and forth from molarity of the hydroxide and the hydronium, that we're going to be using this formula that is the H plus times the hydroxide equals 10 to the minus 14. So whichever one you have, so let's say I want this H plus, that's what I want. Well, that would be 10 to the minus 14 divided by the concentration of the OH minus. If I wanted this one, I would take 10 to the minus 14 and divide. That's not too bad. It's not too bad. So let's set up a little bit of practice then. So let's start off over here with our OH minus, and then here I'll do my H plus, and at the end I'll have my pH. And we're just going to make a table and do some practice. All right, make sort of table. All right, kill off this pen. All right, so I'll start off this one with 10 to the minus 4. I'll put 10 to the minus, oh, let's do 10 here. And down here we'll have a pH of 6. All right, so those are my givens. Let's come in and add in and do these calculations. So here's our two equations that we've got. pH is negative log of H plus. And that one goes back and forth here. The other one we have, I'll stick over to this side, H plus times OH minus equals 10 to the minus 14. And that goes back and forth between these two. Okay, so let's start off then. 10 to the minus 14. Put it right here. 10 to the minus 14 divided by 10 to the minus 4. And we can type that right into our calculator. Now you might have seen the shortcut that this box and whatever my answer in the box, they have to add up to be 14. Now be careful about that shortcut. It's handy on the easy ones when there's nothing in the front here. They won't add up to that when it's stuff in they're more complicated. We'll get to those in a little bit. Those you just type in your calculator. So I'm just going to type this one in. E to the minus 14 second EE minus 14 divided by second EE minus 4. And it's going to tell me 1E minus 10. 10 to the minus 10. Alright? Which 10 and 4 add up to 14. Okay. Now to get the pH, I'm going to take what's in this box. It'll be 10. Or I could type in negative log, and I'm actually going to use second answer, and then that'll give me my 10. Okay. Oh man, that means this one looks very similar. Terrible example, easy to figure out. Let's do this pH equals 6. So this one, I'm going to take my 10 to the minus, and I'm going to take the 6 and put it in this box. And 10 to the minus 6. Since it's a whole number, we're good. Over here, I'm going from that one to this one, so I'm going to take 10 to the minus 14 divided by 10 to the minus 6. That'll be 10 to the minus 8. 10 to the minus 8. Okay. All right. Let's get rid of some of these. Let's try some more complicated ones. And the more complicated, it's actually just as easy to work it as long as you avoid some of your shortcuts. Your shortcuts get you in trouble. So 1.8 times 10 to the minus 5th and 3.2 times 10 to the minus 4th. And pH of 4.6. Alright, so these a little bit more complicated. So coming here, I'm going to do the same idea, 10 to the minus 14, but this time I have to divide it by 1.8 E. I'm going to do my E negative 5 when I type that in. So don't forget to do your EE correctly. So coming over here, clear out. Second EE negative 14 divided by there we go. Second EE divided by 1.8 second EE negative 5. Alright, so that is how I have it typed in. You'll notice I don't have the multiplication sign. I don't have the 10 in front of the E. And so when I hit enter, I'm going to get some number times 10 to the minus 10. E10. So I got repeating 5, so I'm going to put 5.6 times 10 to the minus 10. You'll notice 10 plus 5 is 15, not that minus 14. But if I take 5.6 times 10 to the minus 10 and multiply it by 1.8 times 10 to the minus 5th, I should get 10 to the minus 14. Now, to get to my pH, I'm doing it off the H plus, so negative log of 5.6 E negative 10. Negative log 5.6 second EE negative 10. You could have also just used the previous answer. So 9.3. Okay. So I got this. Remember, it's the log scale when you go up. So when I have 7 being neutral, when I'm at 6, I have 10 times the amount of acid. All right. So this one going this way, 10 to the minus 14 divided by 3.2 times 10 to the minus 4. So second EE minus 14 divided by 3.2 second EE negative 4. And it gave me an error. Let me see what it did. Okay. Clear. Give me an error. Second EE minus 14 divided by 3.2 second EE minus 4. I had hit the 10 to the X instead of the EE button. Alright, so 3.13 purple, terrible. 3.13 3 times 10 to the minus 11. Now 11 plus 4 is my 15 again. All right, so that's expected values. Now on this one, I'm going to do negative log of 3.2 e negative 4. All right, now it should be close to 4. Should be close to 4. But I have 3 times. If it was 1 times 10 to the minus 4, it would be 4. But I have 3 times the amount of acid. All right, my H plus is my acid. If it was if it was 10 times, then I'd go up and it would be 3, 10 times the acid. Remember, acids have less than 7, bases have a pH more than 7. That's just because of that negative sign. Also keep in mind, because of the logarithm, then 14 is as big as we can get because of this 10 to the minus 14 up here. All right, so this one, negative log 3.2 second EE, no, second EE, there we go, negative 4. And it says 3.49. 3.49, not quite halfway, but it's not, see how it's not quite halfway. So we had 3 times there instead of 5 times. Okay, so if we'd had 5 times, we might be exactly at 3.5. All right, so let's do another one. 10, here's my 4.6. First thing I need to do is go to my H plus. So I'm going to do my 10 to the minus, and I'm going to put my 4.6 in the box. Whoa, that looks complicated. So I'm going to hit second log minus 4.6. Alright, and then when I hit enter, it's going to give me my answer. And it said 2.5 times 10 to the minus 5th. Alright, so close to this 5. If this was 5, it'd been close, so not bad. Now I'm going to do second EE minus 14 divided by that answer. In other words, 10 to the minus 14 divided by the 2.5 E negative 5. And so I should get an answer. Now, I'm going to estimate it should be around 10 to the minus 10, and in fact, it's 3.98 times 10 to the minus 10. All right, so those are our 3 skills, going from hydronium concentration to H plus concentration. Just got to be careful. When they tell you this hydronium concentration, they might say 10 to the minus 5 molar HCl. And now they've given you that concentration, but they didn't write it as brackets. They used this capital M. So be careful about those. Practice them. There's only so many combinations. I give you those formulas. They're located on my hopefully equation. All right. So looking at these pH and H plus, they're over here. I also see this pH equals negative log base plus acid. Oh man, I remember hating that, and that's because it's the Henderson-Hasselbalch equation. Oh, we're not going to deal with that. Don't worry about it. All right, we hate that one. Let's see. So neutralization. I want you to memorize this reaction. Then, so it's written out as a base first. So we'll go ahead and do that. A base plus an acid always goes to a salt plus water. Salt plus water. All right, so base plus acid goes to salt plus water. Now, the one that I have given us on our slide here, sodium hydroxide plus HCl, it actually forms the compound sodium chloride, which is salt. Now, that class of compounds is named after that compound, and it is defined in this reaction. But what I'm after then is a base plus an acid goes to a salt plus water. You need to memorize that. All right. Just like when we did combustion, I'll be asking for these products. Okay. A salt plus water. All right, we're ready then for this discussion on buffers. They're a buffer. You take a weak acid and you mix it with its conjugate base. All right, for instance, ammonia and ammonium, carbonic acid and CO2. Um, you can mix not, acetate, sodium acetate, and acetic acid. All right, and that'll make it. So a buffer, what I want you to know about is it resists changes to acids and bases. It resists these changes. Now, a buffer can be overloaded. It doesn't prevent completely these changes. You can have, if you add enough acid, you'll overcome and you'll react all the conjugate base, and now there's none left to react, and then the pH will start changing. All right, but we use buffers in our body a lot. We use buffers all over the place. I always remember it. What was the secret where it's strong enough for a man, but pH balance for a woman. All right. So this idea of buffers, they're ways to control the pH, and we're going to resist those changes. All right. We want to talk about indicators. Indicators are things that change colors under different conditions, and so for us, we're looking at different colors in acid versus base. Um, you can have indicators being drops of liquid. Um, we can have different indicators even on paper, and we make what's called pH paper, where you dip it in your pool, for instance, and you decide you measure it here. We use it a lot in the aquarium industry. Okay, so that'll take us through buffers and indicators. So we're ready for oxidation and reduction. We're on the home stretch here then. Oxidation and reduction. I want you knowing all three of these definitions. All right, so let's look at these definitions. Oxidation and reduction. Your life is made easier if you know all three definitions, because you can apply whichever definition is easiest. So oxidation, the original definition was you gained oxygen. And then a reduction would be losing oxygen, reducing the amount of oxygen. Now the problem with this is some reactions, it's difficult to tell how much oxygen you gained or lost. And so if I had, for instance, let's do C2H6, and I took this and formed C2H4, it's hard to tell if this was an oxidation or a reduction. Well, looking over here, how many things are oxygen? 0. And how many things over here are oxygen? 0. But this one has more things. We started off with more things that aren't oxygen. Now we have less things that aren't oxygen. So the percentage of oxygen went up. And so we oxidized. Ah, terrible, terrible. And so they quickly realized they needed another definition. And so another definition then here would be about the hydrogens. So an oxidation is when you lose hydrogens, and you lose them in sets of 2. And a reduction then will be when you gain hydrogen. And so if you gain hydrogen, then you're also losing oxygen because the percentage of oxygen goes down. It even helps us by having 2 definitions, helps cover cases where we didn't even have any oxygen. All right. Now, what this really came down to was electrons. And so it gave us a way of looking at these without really having any oxygen or hydrogen. So oxidation would be when we lose electrons. There's our symbol for electrons. And reduction is when we gain electrons. And so electrons follow the hydrogens. Whatever the hydrogen is doing, that's what that's going to be doing. All right. Now, when I was a student, I learned this with oil rig. All right, and so it was real common for I'd take my test. I write my name. I write PV equals nRT. I maybe wrote M over dV for my density, and then I'd slap out oil rig every test. Just as I got used to writing that, it became part of my name. Worked great in chemistry tests, not so good on my history exams. Uh, they always looked at me a little funny. All right, so oil rig, oxidation is gaining. Click down here on this. Oxidation, I'm sorry, is losing electrons. Oxidation is losing electrons. Reduction is gaining electrons. And so this is a way to keep up with our electrons. All right. Now, the problem comes in the charges. And so when I look at charges, it causes us problems. Remember, if you have a positive charge, you have lost electrons. And so if you become more negative, you are gaining electrons. Okay? So the way I'm going to look at it is I'm going to look at this charge. So things that are neutral at 0, there's +1, and +2, and +3, and then -1, -2, and so on. -3 down here. All right. And I'm going to think of an elevator. So 0 is my ground floor. Now, if I am losing electrons, I'll be moving up. All right. So I'm losing electrons. I'll be going up, and that's oxidation. Now, if I gain electrons, that's reduction. So, an oxidation, you go up, reduction, you go down. And so, the way I always kept up with it, reduction, you reduce your height or your altitude. All right, you go down, you reduce, and then elevator. It doesn't matter if you're at the ground floor and you go down to -3, or if you were at +3 and you went down to the ground floor to 0. So reduction, you're going down, oxidation, you're going up. This made it click for me in terms of the charges a lot more. All right, it's really a matter of matching the definition to the problem. This magnesium has undergone a reaction, and it went from no charge indicated here, so there's nothing up there, it's 0, to having a +2 charge. Was it oxidized or reduced? Well, the magnesium lost, remember, it went down, right? So it lost electrons, right? And so, sorry, on ours it went up from 0 to +2, so it was oxidized. Okay. Now, the hard part for many students is the fact that when we do these, that they don't happen in a vacuum. That something causes things to be oxidized, and something causes something else to be reduced. And so this idea of oxidizing agents and reducing agents can be a little difficult here, but treat the word agents as if it flips the meaning. And we use the word agent for similar things all the time. A music agent, their job isn't to play music. A sports agent, their job isn't to exhibit their sports. It's to allow someone else to play music or play sports. And so an oxidizing agent, its job is to cause something else to be oxidized. All right? And so how does it do it? Remember, what we're looking at is electrons being transferred. So here in this one, CuO plus H2, all right? This has a +2 charge, this has a -2, and my hydrogen is actually neutral. And so when this reacts, now I have copper that's got no charge, and this one we'll talk about later has understood charge, okay? And so the copper oxide here, copper 2 oxide, this copper gained 2 electrons. It gained 2 electrons. Now, where did they come from? They came from these hydrogens. Right? So hydrogen gave those electrons over to the copper. Notice the oxygen then would be treated as a -2 here, and each one of these has a plus. There's 2 of them. Each one is a +1. All right? And so hydrogen lost the electrons, copper gained them. Now, these numbers over here, water is not ionic. We're treating it as if it's ionic. So to put these numbers, we use these numbers called oxidation numbers. And their definition is terrible. Their definition is, it's the charge something would have if it had a charge. The charge something would have if it had a charge. There's a whole list of rules for those, but for us, we're going to just look at the fact that, hey, this copper was a +2, now it's a 0. We'll treat it as a charge. So we'll treat this as a +1 for each hydrogen and a -2 for the oxygen. That gives us the oxidation numbers. And we just pretend everything is going to be ionic. Remember, we're going to do subscript times charge plus subscript times charge. That'll equal the total charge. And for everything that we do, got cut off there. Everything we do there, it's going to be based off of that. So you can really just look at the electrons being moved. All right. Now, if the copper was being, it went from a +2 to a 0, and so it gained electrons. All right. It was reduced. What caused it to be reduced? It was this hydrogen. All right. And so if it is oxidized, it's automatically the reducing agent. If it's reduced, it's automatically the oxidizing agent. That's just the easiest way to look at it. Okay. So our oxidation numbers, we talked about those. So not too big a deal. So if you can find what's being oxidized and what's being reduced, then they're automatically, if you know what's reduced, then you automatically know what's being oxidized. You'll notice the oxygen was just along for the ride here. Now, I could have done this a different way. I could have done this when I looked at my CuO plus H2. We said this went from a +2 and it went to Cu that was neutral. And it went from a +2 to a 0, and it was reduced because it gained electrons. Let's look at it a different way. How much oxygen is here? How much oxygen is with my copper? 1. How much oxygen is with it down here when it's by itself? None. And so it lost oxygen. If it lost oxygen, it reduced the amount of oxygen. It was reduced. That's why I want you to know all 3 definitions. And so if I know this is reduced, I come over here and I can say this is reduced, which makes it automatically the oxidizing agent. This was oxidized. It had no oxygen. Now it has oxygen. And that makes it the reducing agent. Agent flips the meaning. Alright? Easy enough. Alright, so that takes care of chapter 8. A lot of terms, one skill. Our one skill then was our pH. Okay, so practice those. Study over the definitions here. So acids, bases, oxidations, reductions. Practice the pH problems. They're not super difficult, but you do need to practice them. Alright, we'll catch you on the next one.